6. How the OS tracks processes. To manage all these state transitions, the OS needs data structures. This section covers the two key structures the OS uses to track processes: the process list and the process control block, PCB. You will also see two extra process states beyond the three you already know. The process list tracks all processes. The OS keeps a process list, a data structure that holds every process in the system. Some books call this a task list. The OS uses the process list to know which processes are ready, which are running, and which are blocked. Each entry in the process list is one process control block, PCB. A PCB is a data structure that stores everything the OS knows about a single process. Some books call a PCB a process descriptor. Think about it. The OS must track blocked processes too. When an I/O event finishes, how does the OS know which blocked process to wake up? Building on this, when an I/O event completes, the OS searches the process list. The OS finds the correct blocked process. Then the OS moves that process to the ready state. What a PCB contains. Each PCB holds several categories of information. The most important field here is the register context. The register context stores the saved values of the process's CPU registers. The register context enables stopping and resuming. When the OS stops a process, the OS saves that process's register values into the PCB. The register context holds values like the program counter, stack pointer, and other general-purpose registers. Later, the OS resumes that process. The OS copies the saved register values back into the actual CPU registers. The process continues exactly where it left off. This save and restore technique is the context switch you first saw in Section 1. Here you can see the concrete mechanism. The OS copies register values between the PCB and the CPU hardware. Future chapters cover context switches in full detail. Think about it. The OS saves registers into the PCB and restores them later. What would happen if the OS skipped saving the program counter? Two extra process states, initial and final. Earlier sections described three process states: running, ready, and blocked. Real operating systems also use two more states. The initial state, called embryo in XV6, means the OS is still building the process. The process is not yet ready to run. The OS finishes setup steps like loading code and allocating memory before moving the process to ready. The final state, called zombie in Unix systems, means the process has exited but has not been fully cleaned up. The process finished running. However, the OS keeps its PCB entry around for a specific reason. Why the zombie state exists. A parent process sometimes needs to check whether its child succeeded or failed. Unix programs return 0 to signal success. Unix programs return a non-zero value to signal failure. The zombie state keeps the child's PCB alive after exit. The parent then calls wait to collect the child's return code. After the parent calls wait, the OS finally removes the zombie's PCB from the process list. Think about it. If the OS deleted a child's PCB immediately on exit, the parent could never check the child's return code. Why does that matter for programs that launch other programs? Section Summary. The OS tracks every process through two linked data structures, the process list and individual PCBs. Each PCB stores memory info, register context, I/O info, and process state. The register context lets the OS stop and resume processes through context switches. Beyond running, ready, and blocked, the initial and zombie states handle process creation and cleanup.